Picture yourself on a quiet evening, watching the sun sink toward the horizon. That soft, ordinary warmth on your face that you have felt 10,000 times without a second thought. Now let me tell you that, at this very moment, a small machine is flying straight through the outer atmosphere of that same sun. It is roughly the size of a car. It is moving at 430,000 miles an hour, about 690,000 kilometers an hour, which makes it the fastest object our species has ever built. And it is sitting inside a place so hot that, by every rule we thought we understood, it should not still exist. But it does. It is out there tonight, circling a star, doing something people spent decades calling impossible, flying not near the sun, not close to the sun, but into it. The machine is called the Parker Solar Probe, and over the past few years it has slipped again and again into the sun's outer layers, gone silent for days at a time, and come back each time unburned, carrying home the first close look we have ever had at our own star from the inside. So how does a thing built by human hands travel into a place that reaches 1,000,000 degrees and not melt? That is the question I want to explore. And it begins with something almost everyone gets wrong about the sun, because the real danger was never the surface. I want to start with what actually happened, because on paper it reads more like a dare than a mission. It helps to picture the shape of the mission, because it is not what most people imagine when they hear the words flying to the sun. The probe did not point itself at the star and accelerate in a straight line. It fell, and it looped, and it fell again, tracing a long series of ellipses that grew tighter over the years. Each loop carried it out past the orbit of Venus and then back inward toward the sun, a little nearer every time. So the 2024 record was not a single dramatic plunge. It was the last, tightest turn of a spiral the spacecraft had been drawing patiently since the year it launched. And it is worth holding on to just how alone it was out there. There is no rescue at the sun. There is no turning back, no second attempt if the first one fails. A spacecraft near the Earth can be watched, adjusted, sometimes even repaired by a crew. This one was millions of miles beyond any help, carrying instruments that took years to design and could never be replaced, straight into the one place engineers had spent lifetimes warning each other was off limits. Everything had to work the first time, and keep working, with the star itself trying to undo it. The machine is called the Parker Solar Probe. It launched in 2018 on a heavy rocket rising off the coast of Florida, and it began a journey unlike anything we had attempted before. Its goal was not to fly by the sun and take a few pictures from a safe distance. Its goal was to go in, to fly through the outer atmosphere of a living star and survive long enough to send back what it found there. For 6 years, it circled inward, closer and closer with each loop, until that morning on Christmas Eve, 2024, when it made the closest approach to the sun any object from Earth has ever made. At its nearest, it passed within 3.8 million miles of the sun's surface, about 6.2 million kilometers. Now, 3.8 million miles does not sound close. It is a distance we can barely picture, far larger than anything in our daily lives. The sun is enormous, and the space around it is enormous too. So a number that huge does not feel intimate at all. So let us shrink the whole thing down to something you can hold in your mind. Imagine the distance from the Earth to the Sun compressed to a single foot, about the length of a ruler. On that scale, the entire journey from our planet to the star fits in the span of your hands. And on that same scale, the Parker Solar Probe was sitting less than half an inch from the surface of the Sun. Half an inch out of a foot. That is how close it came. And it was not drifting there gently. It was, and still is, the fastest thing our species has ever made. It was moving at 430,000 miles an hour, about 690,000 kilometers an hour. A number that size is almost meaningless on its own, so hold it against something you know. At that speed, you could travel from New York to Los Angeles, the whole width of a continent, in about 20 seconds. A commercial jet needs around 5 hours to cross that same distance. The probe would cover it before you finished a single slow breath. If you tried to watch it pass, it would already be gone before the image reached your eye. Here is a detail that makes the whole thing feel less like history and more like something happening right now. That first pass in 2024 was not a one-time stunt, a single record set and then retired. The probe has kept going back, again and again. By the end of 2025, it had completed its 26th close approach, on the 13th of December, and each time it returned to that same record edge, 3.8 million miles out, 430,000 miles an hour, holding the line it had drawn. This is not a story about one brave moment in the past. As you listen to this, that same spacecraft is still out there, still circling the sun, still holding the record for the fastest object human beings have ever built. The record has not been broken because nothing else has come close. But there is something worth understanding before we go any further. Speed was never really the hard part. That may sound strange, given the numbers we just walked through, but it is true. Getting something to move quickly near the sun is, in a sense, just a matter of letting the star's own gravity pull it in, fall toward something massive enough, and you will pick up tremendous speed for free. The genuinely hard part, the part that occupied engineers for years, was different. It was building something that could arrive at the sun and not be destroyed outright. Something that could sit inside that furnace and keep working, keep thinking, keep sending its signal home. Hold the speed in your mind one more way, because it is genuinely hard to grasp. 430,000 miles an hour works out to roughly 120 miles every single second. In the time it takes to say the word Mississippi, the probe has already crossed a distance greater than the length of most countries. Nothing else we have ever built moves like this. Rockets, jets, bullets, all of them are slow by comparison. And this is not a brief burst of speed either. It is the pace the spacecraft holds as it whips around the sun at its closest approach, faster than any human creation has gone before or since. And to understand why that was so close to impossible, why serious people spent decades calling it undoable, we first need to correct something almost everyone gets wrong about the sun. Because the real danger was never the part you are picturing. It was not the bright surface at all. It was the thing that floats above it, invisible to the eye, a place far stranger and far hotter than the star beneath it. Ask most people why the sun is dangerous, and they will tell you it is because it is hot. And that is true, as far as it goes. The visible surface of the sun, the bright disk we actually see in the sky, burns at around 10,000 degrees Fahrenheit, which is roughly 5,500 degrees Celsius. That is hotter than anything you will ever touch in your life. It is hotter than the inside of a furnace, hotter than molten rock pouring from a volcano, hot enough to turn any metal you could name into vapor. If that were the whole story, the sun would already be one of the most hostile places imaginable. To feel how upside down this is, imagine walking into a warm house on a cold day. You step through the front door and the entryway is comfortable. You walk down the hall and it gets warmer. You reach the far bedroom, the room farthest from the furnace in the basement, and instead of being the coolest room in the house, it is somehow a blazing 300 times hotter than the furnace that is supposed to be heating everything. You would not believe the thermostat. You would assume something was broken. That is more or less the position solar physicists have been in for the better part of a century, staring at a star that seems to heat its own outer air far more fiercely than the surface below it. For a long time, the puzzle sat almost entirely out of reach, and the reason was simple. To study the corona properly, you have to get to it, or at least point something sensitive enough at it from close range. From Earth, the blinding surface drowns out the faint corona almost completely, except in those rare minutes of a total eclipse. Space telescopes helped, but they still watched from tens of millions of miles away. It was a bit like trying to understand a candle flame by studying it from the far end of a stadium. You can tell it is there. You can measure a few things about it, but the fine detail, the moment-to-moment behavior that would actually explain what is going on, stays just out of view. But the surface, strange as it sounds, is not the strangest part of the sun. Above it lies something called the corona, the sun's outer atmosphere, a faint envelope of gas that reaches millions of miles out into space in every direction. Most of the time you cannot see it, because the blinding surface below washes it out. But you may have seen it without realizing what you were looking at during a total solar eclipse, in those few minutes when the moon slides perfectly in front of the sun and blocks the bright disk. A pale, wispy halo appears around the edge of the darkness, like a crown of soft light. That halo is the corona. For most of human history, those brief eclipses were the only chance we ever had to glimpse it at all. And this is where the sun stops behaving the way our instincts insist it should. You would expect the corona, floating above the surface and farther from the sun's core, to be cooler than the surface below it. It is not. It is hotter, not slightly hotter, dramatically hotter. While the surface sits at around 10,000 degrees, the corona reaches temperatures between 1 and 3 million degrees Fahrenheit. That is up to 300 times hotter than the surface directly beneath it. The thin outer air of the sun is hundreds of times hotter than the blazing ball of fire it surrounds. Sit with that for a moment, because it quietly breaks one of the most basic rules we live by. Stand next to a campfire on a cold night. The closer you lean in, the warmer you feel. The farther you step back, the cooler it gets. Heat fades with distance. Every one of us has felt this 1,000 times. It is one of the first things a child learns about the physical world. Yet at the sun, the exact opposite happens. Move up from the surface, out and away from the source of all that energy, into the corona, and the temperature does not fall. It climbs. it soars. It is as if you walked away from the campfire and felt the air grow hotter with every step. Physicists have a name for this contradiction. They call it the coronal heating problem, and for more than 80 years, it has stood as one of the great unsolved mysteries in all of astronomy. Something up there is pouring energy into that thin outer air, and for the better part of a century, no one could say for certain what. There is a fair question hiding inside all of this, and people ask it often, so let us not skip past it. How do we even measure a temperature of 1,000,000 degrees? We are obviously not lowering a thermometer into the corona. Nothing we could build would come back. The answer is that temperature, at this scale, is really a measure of how fast particles are moving, and we read that speed in light. When atoms in the corona get hot enough, they are stripped of many of their electrons, and each of these stripped-down atoms gives off light at very specific colors that can only appear at extreme temperatures. Iron that has lost more than a dozen of its electrons, for example, glows in a particular way that iron never can at ordinary heat. So when we point our instruments at the corona and see that exact signature of light, the corona is, in effect, telling us its own temperature, not by touch, but by the color of what it emits. We are reading the heat in the glow, and the mystery runs deeper than a single strange jump in temperature. Just above the surface of the sun lies a remarkably thin layer, only about 100 kilometers thick, a sliver on the scale of the sun. It is called the transition zone. Cross that narrow band, and the temperature leaps from a few thousand degrees to hundreds of thousands of degrees within that thin layer alone. It is one of the sharpest changes anywhere in the solar system, and it happens in a space that, in cosmic terms, is almost paper thin. We have theories about how it forms and why it behaves the way it does, but no one has ever been able to watch it closely enough, from near enough, to be sure. And this is the mystery the whole mission was built to chase down. Something up in the corona is dumping energy into that thin gas, heating it far beyond the surface below. And for decades, the candidates were only guesses. Was it waves rippling up through the sun's magnetic field? Was it countless tiny magnetic explosions, too small to see from afar, but adding up to enormous heat? Each idea had its supporters, and none could be confirmed, because confirming any of them required getting close enough to catch the process in the act. The answer, whatever it was, lived in a place no instrument had ever visited. For decades, this was as far as we could get. The corona could be studied from a distance, through telescopes, during eclipses, from spacecraft in orbit near the Earth, but never from within. And a mystery you can only observe from far away is a mystery that tends to stay a mystery. To actually solve it, something would have to go in and measure the corona directly, from the inside. But this same superheated, puzzling place is also the reason the whole question matters far beyond the sun itself. Because it is out of this 1,000,000-degree atmosphere that something is born, something that does not stay near the sun at all, but streams outward across the solar system and washes over our own planet every hour of every day. But how did we even know the corona was so strangely hot in the first place? Before anyone dreamed of flying a machine into it, they had to first realize there was a mystery there at all. And the story of how we figured out that the sun's outer atmosphere is impossibly hot is one of the strangest detective tales in the history of science, a puzzle that took the better part of a century to crack, and that turned up a brand new element along the way. It begins, fittingly, in the fleeting darkness of total eclipses. For centuries, those few minutes when the moon covers the sun were the only chance astronomers had to study the faint corona at all. And when they began pointing early instruments called spectroscopes at that pale halo, instruments that split light into its component colors, revealing which elements are present, they started seeing things that did not make sense. In 1868, during an eclipse observed from India, the French astronomer Jules Janssen caught a bright yellow line in the sun's light that matched no known substance on Earth. The English astronomer Norman Lockyer saw the same line and reached a bold conclusion. It must come from an element that existed in the sun but had never been found on our own planet. They named it helium, after Helios, the Greek word for the sun. Sit with how remarkable that is. Helium, the second most common element in the entire universe, the gas in every party balloon, was discovered on the sun 27 years before anyone found a trace of it on Earth. It was, in a real sense, the first alien element, spotted in a star, before it was ever held in a hand. Then the corona produced a mystery of its own. During eclipses in the 1800s, astronomers found yet another unexplained bright line in the coronal spectrum, one that again matched nothing known. Following the pattern that had worked with helium, they assumed it must be another new element, one that lived in the sun's atmosphere, and they gave it a name: coronium. For decades, coronium sat in the textbooks as a genuine puzzle, a supposed element that stubbornly refused to appear anywhere on Earth. But coronium was a ghost. The truth, when it finally came, was stranger than a new element would have been. In 1939, the astronomer Walter Grotrian, building on work by the physicist Bengt Edlund, realized that the mysterious coronium line was not a new element at all. It was ordinary iron, but iron stripped of 13 of its electrons. And here is why that mattered so much. To tear 13 electrons off an iron atom, you need staggering energies. Iron can only reach that state at temperatures of 1 to several million degrees. The faint coronium line was not announcing a new substance. It was quietly announcing a temperature, and that temperature was impossibly, inexplicably high. It is worth pausing on how much patience this kind of science demands. The clue that would eventually crack the mystery, that single coronium line, had been sitting in astronomers' notebooks since the 1860s. For 70 years, people looked right at it and drew the wrong conclusion, because the right conclusion was almost too strange to consider. Nobody wanted to believe that the thin outer air of the sun could be hundreds of times hotter than the blazing surface beneath it. The data was there the whole time. What was missing was the willingness to accept what it was saying. Science often works like that, not a sudden flash of insight, but a long, stubborn wait for the world to make sense. And it is worth appreciating the strangeness of that whole chain of reasoning, because it shows how indirect our knowledge of the sun has always been. No one ever put a thermometer near the corona in those years. They read a color of light, matched it to iron missing 13 electrons, and from that single fact, deduced a temperature of millions of degrees. It is a little like walking into a room, seeing a particular scorch mark on the wall, and concluding from that mark alone that a furnace must have burned there. The corona never told us its temperature directly, We had to infer it, cleverly and stubbornly, from the faint traces it left in its light, and even then, it took decades to trust what those traces were saying. That was the moment the coronal heating problem was genuinely born. The corona was not a gentle outer glow. It was millions of degrees hotter than the surface below it, and no one had the faintest idea why. The mystery had been hiding in plain sight, written in a single line of light that people had been staring at and misreading for 70 years. From that point on, solving the puzzle of the sun's superheated crown became one of the great goals of solar physics, a goal that would, decades later, help justify the most audacious idea of all, sending something in to measure it directly. So why does any of this reach us at all? The corona does not just sit there glowing, it leaks. Out of that million-degree atmosphere, a steady stream of charged particles flows outward in every direction, filling the entire solar system with a thin, invisible breath from the star. This is the solar wind, and it never stops. It is not a rare event or an occasional gust. It is a constant, ongoing river of particles pouring off the sun at all times. It is blowing past Earth at this very moment, as you listen, at speeds somewhere between 200 and 500 miles a second. Not miles an hour, miles a second. The solar wind crosses the distance from the sun to the Earth in a matter of days. Think about what that river of particles has to pass through to reach us, and how far it travels. The solar wind leaves the sun and spreads outward in every direction, thinning as it goes, until it washes over the planets one by one. By the time it reaches Earth, it has crossed about 93 million miles of space, and still it arrives with enough energy to matter, because there is so much of it, and it never lets up. Our planet has been standing in this wind for billions of years, sheltered by its magnetic field, quietly protected from a force most of us never think about even once. It is worth being clear-eyed about the risk, without overstating it. Most solar storms are mild, and most of the time the worst you will notice is a beautiful display of northern lights pushed farther south than usual. The concern is the rare, powerful event, the kind that comes along once in a great while, but arrives with enough force to overwhelm the systems we have built. We now live in a civilization stitched together by satellites, timing signals, and long metal power lines, and those are exactly the things a severe solar storm can disturb. Understanding the sun, then, is partly about wonder, and partly about knowing our own weather from the star we orbit. Most of the time, we never feel it, and there is a good reason for that. Our planet carries its own shield. Earth has a magnetic field generated deep in its molten core that wraps around the entire planet like an invisible cocoon. When the solar wind arrives, this field deflects it, steering the stream of particles around us the way a boulder in a river parts the water flowing past. We live our whole lives inside that protection, mostly unaware it is even there. It is one of the quiet reasons life on Earth is possible at all. But the sun does not always breathe gently. Sometimes it does something far more violent. It can hurl out a sudden, enormous eruption of magnetized plasma, a coronal mass ejection, billions of tons of charged material flung into space in a single burst. When one of these is aimed our way and strikes the Earth's magnetic field hard enough, it can shake the whole cocoon. And the effects of that are real, and they are not always gentle. A strong enough storm can knock satellites offline, scramble the signals that GPS depends on to tell us where we are, disrupt radio communication across whole regions, and push damaging surges through the power grids that run along the ground. The very same physics that paints the northern lights across a winter sky, those beautiful curtains of green and red, can, in its more violent moods, threaten the machinery that modern life quietly depends on. And there is a reason this feels especially urgent right now, at this exact moment in time. The sun is not steady from year to year. It runs on a roughly 11-year cycle of activity, swinging between quiet stretches and stormy ones. Right now, it is near the peak of that cycle, a period scientists call solar maximum, when eruptions come more often and hit harder than usual. The Parker Solar Probe is gathering its data at precisely the moment the sun is at its most restless and most active. It could hardly have arrived at a better time to watch the star misbehave. So studying the sun this closely is not an abstract exercise in curiosity, something that matters only to scientists. It is, in a very direct and practical sense, about protecting the satellites, the grids, and the systems that our whole civilization now leans on. There is something humbling in realizing how much of this has been going on, unnoticed, our entire lives. Every day you have ever lived, the sun has been breathing this wind past the earth, and the planet's magnetic field has been quietly turning it aside. We feel none of it. We go about our days without a thought, for the invisible storm the sun keeps blowing in our direction, or for the shield of magnetism that makes our comfortable, ordinary lives possible. The probe's work is, in part, an effort to understand a relationship between the Earth and the sun that has shaped life here since long before there were people to notice it, which is exactly what makes the machine sent to do this work so remarkable. And before we look at how it was built to survive the impossible, there is a human story worth telling first, because this spacecraft carries a name, and the story of that name almost never happened at all. In 1958, a young astrophysicist named Eugene Parker sat down and wrote a scientific paper arguing something that sounded, at the time, faintly absurd. He proposed that the sun was not a quiet, static ball of light, but a star that was constantly streaming charged particles outward through the entire solar system, a continuous, ongoing wind blowing from its surface. He called it the solar wind. It was a quiet idea with enormous consequences, and the scientific establishment of the day was not ready to hear it. There is a lesson tucked inside Parker's story that has nothing to do with the sun, and it is one scientists still tell each other. A good idea can be right and still be turned away, at least at first, because it does not fit what everyone already believes. The solar wind sounded wrong to the experts of the day, precisely because it was new. What saved the idea was not that it shouted louder, but that one editor was willing to let it be published and tested. And then reality settled the matter, the way reality tends to, not by argument, but by measurement. It also tells you something about how seriously this mission was taken from the very start. Naming a spacecraft after a living person was not a casual gesture. It was NASA signaling, before the probe had even left the ground, that this was considered one of the most important journeys the agency had ever attempted, a mission to answer questions that a man had first raised 60 years earlier, questions that had waited that whole time for the technology to catch up to them. When Parker submitted his paper to a leading physics journal, the response was not encouragement. A reviewer, a well-respected scientist, rejected it, writing that the idea contradicted established physics and should not be published at all. And by the ordinary rules of science, that could easily have been the end of it. A rejected paper from a young researcher, filed away and forgotten. But the paper had a second chance, and it came from an unlikely place. The journal's editor was a man named Subrahmanyan Chandrasekhar, a figure who would later win the Nobel Prize in Physics. Chandrasekhar reviewed the situation, overruled the rejection, and published Parker's paper anyway. 2 years later, spacecraft measurements settled the argument completely. The solar wind was real. It existed exactly as Parker had described it, blowing through space just as he said it would. The young man with the absurd idea had been right all along. Over the following decades, Eugene Parker went on to become one of the most important figures in the entire study of the sun. His name became woven into the science itself. So when NASA finally prepared to send a spacecraft directly into the sun's atmosphere, the very region Parker's solar wind is born from, it decided to do something it had never done before in its entire history. It named the mission after a living person. Every spacecraft before had been named for gods or concepts or people long gone. This one would carry the name of a man who was still alive to see it fly. And there is a quiet detail here that is easy to pass over, but worth pausing on. Parker was 91 years old when the probe launched. He traveled to Florida, and he stood there, and he watched the rocket carrying his own name climb up into the sky and disappear toward the star he had spent his life trying to understand. He lived until 2022, long enough to see the spacecraft begin to transform our knowledge of the sun. And there is one more small, human thing aboard the probe itself. Bolted to the machine is a memory card, and on it are images of Eugene Parker, along with a copy of that original 1958 paper, the very idea that had once been rejected, now flying at 400,000 miles an hour into the star it dared to describe. The rejected theory made it to the sun after all. Picture the moment for a second. A man in his 90s who as a young researcher had been told his best idea was wrong, standing on the Florida coast, watching a rocket carry that very idea and his own name up toward the star he had argued about for a lifetime. Few scientists ever lived to see anything like it. The theory that had been rejected on paper was now, decades later, being flown bodily into the sun to be tested at its source. There is a rare kind of completeness in that, a life's work coming full circle in a single launch. There is one more thread worth pulling here, because it shows how long this dream had been waiting. The idea of sending a probe to the sun did not begin in the 21st century. It goes all the way back to 1958, the very same year Parker published his solar wind paper. That year, a committee of the United States National Academy of Sciences drew up a wish list of missions for the dawning space age, and on it was a proposal for a solar probe to fly in close and measure the particles and fields near the sun directly. The idea was there almost from the moment humanity could put anything into space at all, and then it waited. It waited 60 years. Not because anyone forgot about it, but because the technology to survive the trip just did not exist yet. The heat shield, the autonomous pointing, the materials. Study after study through the following decades reaffirmed how important the mission would be, and then set it aside as too hard, too costly, too far ahead of what could be built. The spacecraft that finally launched in 2018 was the answer to a question that had been sitting open for 6 decades. Naming a spacecraft is one thing. Building one that can survive inside a star is another problem entirely, and it is the problem that came closest of everything in this story to being genuinely impossible. To see how bold Parker really was, I think we have to look back at what came before it. Parker did not arrive at the sun out of nowhere. It was the boldest step in a long line of missions that had been creeping toward our star for more than half a century, each one learning a little more, each one getting a little braver. To appreciate how far Parker went, it helps to remember the spacecraft that went before it. The first real pioneers were a pair of probes called Helios, built together by Germany and the United States, and launched in the mid-1970s. For their time, they were astonishing. In April of 1976, Helios 2 swung to within about 26.5 million miles of the Sun, closer than any spacecraft had ever been, and closer than the planet Mercury. In doing so, it also became the fastest human-made object of its era, racing along at over 150,000 miles an hour. For nearly half a century, those two records stood. If you had asked, through the 1980s, 90s, and 2000s, what the closest and fastest thing we had ever built was, the answer was still Helios 2, set back in the disco era. Then came a mission with a completely different kind of daring. In the 1990s, a joint European and American probe called Ulysses did something no spacecraft had done before. It flew up and over the poles of the Sun. Every other probe had orbited more or less in the flat plane where the planets circle. Ulysses broke out of that plane entirely, swinging above and below the star to look down on its poles for the first time. It revealed that the solar wind behaves differently over the poles than it does around the equator, and that the Sun's magnetic field is stranger and more lopsided than anyone had assumed. It gave us our first true three-dimensional sense of the wind blowing off our star. And then there is the quiet, long-lived workhorse that many people have relied on without ever knowing its name. In 1995, Europe and the United States launched an observatory called SOHO, positioned far out in space, where it could stare at the sun without interruption. It was meant to last a few years. It has now watched the sun for decades, becoming the longest-lived sun-watching mission in history, and along the way, it has spotted more than 5,000 comets, many of them diving toward the sun, making it almost by accident the most successful comet hunter of all time. To this day, when forecasters warn of a solar storm heading for Earth, much of that early warning traces back to SOHO's steady vigil. It is worth pausing on how long those old records stood, because it says something about how hard this problem really was. Helios 2 set its marks in 1976. That is before most people listening to this were born. Across all the decades that followed, through the space shuttle, through the building of the space station, through the rise of the internet and the smartphone, no spacecraft got closer to the sun or moved faster than a probe from the mid-1970s. It was not for lack of ambition. It was that the wall between us and the sun was made of heat, and until we learned how to build something that could pass through that wall, the record could not be broken. Parker did not just inch past Helios. It ended a reign that had lasted almost 50 years. Each of these missions had a hard limit though, and it was always the same one: heat. They could fly toward the sun, or over it, or watch it from a safe distance, but none of them could go in. Helios came closest, and even Helios stopped tens of millions of miles short of the corona, because the technology to survive any nearer did not yet exist. This is what makes Parker's leap so dramatic. It did not just edge past the old records, it shattered them, flying roughly 7 times closer to the sun than Helios ever managed, and moving nearly 3 times faster. The spacecraft that had spent decades as the champion was left far behind. Everything the earlier missions had learned from a distance, Parker was finally built to go and measure from within. So how do you build a machine that can sit inside a star and not be destroyed? Here is the core of the engineering problem, laid out plainly. At its closest passes, the sun-facing side of the Parker Solar Probe reaches temperatures of around 2,500 degrees Fahrenheit, roughly 1,370 degrees Celsius. Let that number settle. That is hotter than flowing lava. It is hot enough to melt steel, to melt aluminum, to melt titanium, to melt very nearly any metal a person might think to build a spacecraft from. By any ordinary logic, a machine facing that heat should slump, warp, and vanish. And yet, just a few inches behind that blazing front surface, the scientific instruments doing the actual work, the cameras, the sensors, the delicate electronics, sit at about 85 degrees Fahrenheit. That is close to comfortable room temperature. On one side, a temperature that melts metal. A few inches away, a mild spring afternoon. And the entire gap between those two worlds is bridged by a single piece of material, only about 4.5 inches thick. It is worth dwelling on just how counterintuitive the whole design is. Our instinct, faced with tremendous heat, is to reach for something strong and solid, thick metal, dense armor, the sturdiest material we can find. But metal is exactly the wrong answer here, because metal conducts heat beautifully. It would soak up the sun's energy and carry it straight through to the delicate instruments behind. The winning move was almost the opposite of armor. It was to build something mostly out of nothing, a lightweight sandwich of carbon around a core of near-empty foam, engineered so that heat has almost no way to travel across it. Sometimes the strongest shield is the emptiest one. And consider the strange, split existence of the spacecraft during a close pass. One side of it, the face turned toward the sun, glows at a temperature that would melt a steel beam. A few inches away, on the sheltered side, the electronics hum along in what amounts to a mild room. The machine lives in 2 utterly different worlds at the same moment, separated by that thin disk of carbon. It is a little like standing at a doorway with a raging furnace on one side and a cool spring evening on the other, and feeling both at once and being fine, as long as you never, ever turn around. There is also something quietly clever in the choice of white paint on the sun-facing side. It seems almost too small to matter against a star, but color is doing real work. A dark surface drinks in light and turns it into heat. A white surface throws much of that light back before it can ever be absorbed. It is the same reason people wear light colors on a hot day. Scaled up and refined for a spacecraft, that ordinary intuition becomes one more layer of defense, bouncing away a large share of the sun's energy before the shield behind it has to deal with the rest. That piece is the heat shield, formerly called the thermal protection system, and it is one of the most elegant things NASA has ever built. It is a disc a little over 2 meters across, about 8 feet, and its design works like a sandwich. On the outside, 2 thin panels of a tough material called carbon-carbon composite, and pressed between them, a core made of carbon foam. On Earth, that foam is about 97% air, which is why the whole thing weighs almost nothing for its size. And that leads to a detail that genuinely surprises people when they first hear it. The entire disk that stands between the spacecraft and the Sun weighs only around 160 pounds, roughly 70 kilograms. That is about the weight of a single adult person. A shield light enough that you could imagine carrying it, and it is the only thing holding a star at bay. And there is a subtlety hidden in that foam that is worth slowing down for, because it is where a lot of retellings get the physics slightly wrong. On the ground, yes, the foam is full of air, but once the probe is out in the vacuum of space, that trapped air escapes, and the tiny pores inside the foam are left holding almost nothing at all, close to a pure vacuum. And that is not a defect. It is the whole trick. Empty space is one of the best insulators there is. Heat needs particles to travel through. It moves by making one particle jostle the next. Where there is almost nothing to carry it, heat has a very hard time crossing it all. So the near emptiness inside that foam is doing real work, quietly blocking the sun's fury from reaching the far side. On top of that, the sun-facing surface of the shield is sprayed with a specially made white coating, designed to reflect most of the incoming sunlight straight back out into space before it can ever be absorbed in the first place. Put it all together, and what the shield creates is essentially a wall of temperature, a steep cliff of heat across just 4.5 inches. The front face may sit near 2,500 degrees, while the far side, only inches away, stays hundreds of degrees cooler, and the instruments tucked behind it rest in near comfort. And the engineers did not build it to barely survive. The shield was tested to withstand up to 3,000 degrees Fahrenheit, meaningfully hotter than anything the sun has actually thrown at it, which means that through every one of its record passes, the shield has been holding a margin in reserve. It is built for worse than it has ever faced, and it has never once been pushed to its limit. But a shield like that only works if it is always precisely pointed at the sun. Let the spacecraft drift even a little, let it turn a few degrees off center, and the sunlight would spill past the edge of the shield and strike the delicate body hidden behind it, and that would be the end. So the probe carries a set of sensors whose only job is to watch for exactly that. If any stray sunlight begins to creep around the edge, the sensors detect it and immediately nudge the craft back, tucking it once more into the safety of its own shadow. It does this automatically, on its own, thousands upon thousands of times, keeping the instruments hidden behind the shield through every single pass, without anyone on Earth having to lift a finger. And keep in mind the margins these engineers were working with. There is no room for a partial success here. If the shield failed even briefly, if the spacecraft turned a few degrees too far and let sunlight slip past the edge for too long, the delicate instruments behind it would be cooked in moments, and the mission would end. Everything depended on this one disk of carbon holding the line, pass after pass, year after year, with no maintenance and no second chances. That it has done so again and again is one of the quiet triumphs of modern engineering, a piece of hardware doing something close to miraculous and making it look almost routine. The shield, then, answers one question: how the spacecraft survives the heat pressing physically against it. But it leaves a deeper question completely untouched, because the corona is 1,000,000 degrees. And 1,000,000 degrees, by everything we think we know, should annihilate anything that enters it, shield or no shield. The reason it does not comes down to a distinction that most of us have never had a reason to think about. It is the difference between two words we tend to treat as the same. You might wonder what makes Parker so different from the probes that came before it. The heat shield is the part that gets the attention, and rightly so, but it is only one piece of a much larger rethinking of how a spacecraft can be built to survive a star. To see how far the engineering had to come, it helps to compare Parker with the older probes that tried to get near the Sun, because the difference is not a small refinement. It is a generational leap. Consider the earlier Helios probes of the 1970s. Their strategy for handling heat was, by today's standards, almost brute force. They spun rapidly, about once every second, so that no single part of the spacecraft stayed pointed at the Sun for long, and they relied on polished, mirrored surfaces to bounce heat away. It worked, but only well enough to get so far, and no closer. That whole approach reached its limit tens of millions of miles from the Sun. To go 7 times nearer, Parker needed something fundamentally different, not spinning and reflecting, but actively managing heat as it flowed. That starts with the shield material itself. The carbon-carbon composite in Parker's shield belongs to a family of ultra-high temperature materials that trace their roots back to earlier eras of spaceflight, including the reinforced carbon used on the leading edges of the space shuttle, where the craft met the fiercest heat of re-entry. But Parker took the idea further, pairing those tough carbon panels with a core of carbon foam that is almost entirely empty space. It is a material that is at once strong enough to survive the trip and light enough to be flung around the Sun at hundreds of thousands of miles an hour, a balance the older probes never had to strike because they never tried to go so fast or so close. Then there is the cooling. Behind the shield, Parker carries something surprisingly humble: water. The spacecraft circulates about a single gallon of water through its systems, and that water absorbs heat and then radiates it away into space, keeping the electronics at their mild working temperature. It sounds almost too ordinary for a mission like this, and that is part of its elegance. Where the old probes relied on mirrors and spin, Parker uses a genuine, actively pumped cooling loop, a small, closed circulatory system for a machine flying through fire. The solar panels tell the same story of cleverness under pressure. A spacecraft needs sunlight to make power, but near the Sun, there is far too much of it, enough to destroy ordinary panels outright. Parker's answer is to keep its main solar array tucked safely in the shadow of the heat shield during the closest passes, extending only a small secondary wing out into the light, and even that little wing is cooled by fluid to keep it from overheating. The panels lean out just enough to catch the power they need, and no more, retreating from the very star they draw their energy from. Above all, Parker is astonishingly independent. Its team has described it as the most autonomous spacecraft ever flown, and it has to be. At its distance, with radio signals taking minutes to arrive, there is no flying it by remote control through a close pass. So the spacecraft watches over itself. Sensors ring the edge of the shield's shadow, and if any of them catch even a sliver of direct sunlight, the onboard computer swings the craft back into cover on its own, in an instant, without waiting to ask Earth what to do. It is less a puppet on a string than a machine trusted to keep itself alive. The achievement was recognized on the ground too. In 2025, the Parker team was awarded the Collier Trophy, one of the most prestigious honors in all of aviation and spaceflight. There is a lesson in this, worth carrying beyond spaceflight. We often imagine that surviving something extreme is about raw toughness, about being harder, denser, stronger than the thing that threatens you. But Parker survives by being clever rather than merely tough. It is light where you might expect heavy, mostly empty where you might expect solid, and it wins its battle with the sun not by outmuscling the heat, but by outmaneuvering it, reflecting what it can, insulating against the rest, cooling what slips through, and hiding everything delicate in a sliver of shadow. The most extreme environment in the solar system is met not with brute force, but with a kind of quiet ingenuity. Put all of it together, the shield, the water cooling, the retreating panels, the self-protecting mind, and you start to see that Parker is not just an older idea, flown a little closer. It is a different kind of machine, one that had to be reinvented almost from the ground up before it could do what the pioneers of the 1970s could only dream of. Now we come to the part that catches almost everyone off guard, and it is the key I find most beautiful in this whole story, because it unlocks how the probe survives at all. The corona is over 1,000,000 degrees. The spacecraft flies straight through it, and still, it does not vaporize. That sounds like a contradiction, like something that cannot be true. To see why it is true, we have to separate two ideas that, in everyday life, feel like the exact same thing: temperature and heat. This single distinction, temperature versus heat, is quietly one of the most useful ideas in all of physics, and once you have it, you start seeing it everywhere. It is why you can wave your hand quickly through a candle flame without harm, but must never hold it there. It is why a dry sauna at 200 degrees is bearable, while a splash of 200-degree water would send you to the hospital. In each case, the temperature is high, but what actually hurts you is how much heat gets delivered, and how fast, and that depends on how many hot particles are there to deliver it. So when you hear that the corona is 1,000,000 degrees, it is worth mentally translating that number. It does not mean 1,000,000 degrees of the kind that would instantly incinerate you if you stood in it. It means the individual particles are moving with the energy that corresponds to 1,000,000 degrees, but they are spread so thin that the total heat in any given space is modest. The sun's outer atmosphere is, in a sense, blisteringly hot and nearly weightless at the same time. That is the paradox the probe was built to fly through, and it is exactly why a 4.5-inch shield is enough to cross it. They are not the same. Temperature is a measure of how fast the individual particles in something are moving. Heat is a measure of how much energy those particles actually hand over when they strike something else. And the reason those two can come apart so dramatically is that one more thing matters enormously: how many particles there are. Let us make this concrete with something from your own kitchen. Picture your oven turned up to 400 degrees and fully preheated. You can open the door and reach your bare hand into that 400-degree air for a moment, and you will feel warmth, but you will not be hurt. People do it all the time. Now picture the steam rising off a pot of boiling water. That steam is only about 212 degrees, far, far cooler than the oven. And yet, if you hold your hand in that steam for even a second, it will scald you badly. Stop and think about how strange that is. The cooler thing burns you, and the hotter thing does not. How? So what is going on? The answer is density. The steam, though cooler, is thick with water molecules, and every single one of them slams into your skin and dumps its energy there. The oven air, though hotter, is thin. There are relatively few particles in it, so even though each one is moving faster, there are not nearly enough of them to deliver much heat to your hand before you pull it back. Temperature tells you how fast, heat tells you how much gets transferred, and density is the bridge between them. Now take that same idea and push it to the far edge of possibility. That is the corona. Yes, each individual particle out there is moving with staggering energy. That is exactly what 1,000,000 degrees means. Particles racing at enormous speeds. But the corona is also very close to a vacuum. It is thinner than almost anything we can create in a laboratory on Earth. There are so few particles in any given pocket of space that, even though each one is scorchingly hot, there are not nearly enough of them to pour real heat into the shield. And so the spacecraft is not swimming through a 1,000,000-degree bath, the way you might imagine. It is gliding through a 1,000,000-degree near emptiness. Each particle it meets is furious, but there are so few of them that a well-built carbon shield can shrug the encounter off. Once you see the difference between temperature and heat, the impossible quietly rearranges itself into something that makes sense. It is worth pausing to appreciate how much this one insight rescued. Without it, the entire mission would look like fantasy, a spacecraft casually flying through a 1,000,000-degree furnace and somehow not caring. With it, the impossible becomes almost ordinary engineering. The corona is ferociously hot in the sense that its particles move at tremendous speeds, but it is so thin, so close to empty, that it just cannot pour that heat into a well-designed shield fast enough to matter. Grasp that, and you understand not just how this one probe survives, but something fundamental about what heat really is. So the probe had its shield, and it had the physics of the near vacuum working in its favor. But knowing it could survive at the sun is a different thing from actually getting it there. And reaching the sun, as it turns out, is far harder than pointing a rocket and letting go. You might assume that flying to the sun is the easy part. Just point your spacecraft at it and let go, and gravity pulls you the rest of the way. It seems obvious, but it does not work like that at all, and the reason is a little counterintuitive, so it is worth walking through slowly. There is a beautiful economy to using a planet as a brake. The probe did not carry enough fuel to slow itself down by force. No spacecraft could. Instead, each time it swung past Venus, it handed a little of its speed to the planet and took a slightly tighter orbit in return. Venus is so enormous compared to the tiny probe that it never noticed the exchange, yet for the spacecraft it made all the difference. Over 7 encounters, spread across 6 years, Those small trades added up to a completely transformed path, a slow, patient tightening that no rocket engine could have achieved on its own. It is easy to rush past how much patience this demanded. 6 years is a long time to spend just getting into position. There were no dramatic images in those early years, no headlines, just a spacecraft looping quietly through the inner solar system, trimming its orbit a little at a time, doing science along the way, while it waited to reach the distances it was genuinely built for. The mission was a lesson in delayed reward. Everything the world would eventually marvel at depended on those unglamorous years of careful, incremental approach. So why can't we just fall straight in? Everything we launch from Earth is already moving sideways at tremendous speed, not because of the rocket, but because of the Earth itself. Our planet is racing around the sun at about 67,000 miles an hour, and everything on it and everything we launch from it inherits that same sideways motion. So when a spacecraft leaves Earth aimed at the sun, it does not travel in a straight line toward it. It carries all that sideways speed along for the ride. And the result is that if you aim straight at the sun and let go, you do not fall in. You sail right past it and swing out into a wider orbit on the far side, missing the target completely. To actually fall toward the sun, you have to get rid of a huge amount of that sideways speed, and shedding that much velocity is one of the hardest things to do in all of spaceflight. In a very real sense, it is harder to fall into the sun than it is to leave the solar system altogether. The solution was as clever as the problem was stubborn. Rather than fighting its own speed with fuel it did not have, the probe borrowed gravity from another world. It used Venus, not as a destination to visit, but as a brake to lean on. Over the course of 6 years, the Parker solar probe flew past Venus 7 separate times, and on each pass, it used the planet's gravity to bleed off a little more of its sideways speed, letting its orbit sink tighter and tighter around the sun. Picture slowly reeling in a fishing line, drawing the loop in a little more with every turn of the reel. That is what those Venus flybys did. With each one, the spacecraft reached a new record for its closest approach, swung back outward, and then fell inward again, nearer to the sun than it had ever been before. And the probe was not merely commuting during those 6 years. It was already making discoveries along the way. It found that the solar wind close to the sun is far more turbulent and complicated than anyone had expected. Not a smooth outward flow, but a churning, restless thing. It detected strange, sharp reversals in the sun's magnetic field, sudden zigzags where the field seemed to double back on itself. Scientists nicknamed these switchbacks, and the probe found them in far greater numbers than any model had predicted. That was a puzzle in itself, and one the mission would keep chewing on. In the years since, researchers have even begun to trace where these switchbacks are born, in patches on the visible surface of the sun, where the magnetic field funnels together and bunches up. On top of all that, the probe flew directly through vast coronal mass ejections, those billion-ton eruptions, and measured them from the inside, something no instrument had ever done before in history. And the discoveries made during those approach years were not minor footnotes. The switchbacks alone reshaped how scientists think about the sun's magnetic field, and the up-close measurements of eruptions gave them their first inside look at events they had only ever seen from a distance. In a sense, the mission was already succeeding long before its record-breaking passes, gathering data no one had ever collected as it spiraled steadily inward. The journey to the sun was, in itself, a voyage of discovery. The seventh and final flyby of Venus came in November of 2024. After that, the reeling in was over. There was nothing left to do but let the spacecraft fall toward the sun on its closest pass yet, and wait for Christmas Eve. On the morning of the 24th of December, 2024, while much of the world was settling into the warmth of the holiday, the team at the Johns Hopkins Applied Physics Laboratory in Maryland was doing no such thing. They were at their consoles, quiet and focused, watching the last streams of data trickle in before their spacecraft went dark. They had spent more than a decade of their lives building toward this single pass, and now all they could do was watch it begin. It is one thing to describe a communications blackout in the abstract. It is another to sit with what it actually meant for the people in that room. These were engineers and scientists who had, in many cases, given a decade of their working lives to this one machine. They knew every system on it, every point where something could fail, and now it was in the most dangerous place it would ever be, and there was nothing left for them to do. No button to press, no command to send, no way to help. All the years of work had already been done. The mission was, for those hours, entirely out of human hands. There is a particular kind of quiet that fills a room in a moment like that. Not the quiet of boredom, but the quiet of people waiting on something they cannot influence. The spacecraft was either going to survive its closest pass, or it was not, and the outcome had, in a sense, already been decided by the design work of years past. The team was just waiting to learn which reality they were living in, and the sun, indifferent to all of it, kept the answer to itself for 2 long days. As the Parker Solar Probe fell toward its closest approach, it crossed into a zone from which no signal could reach us at all. This close to the sun, the raw electromagnetic roar of the corona overwhelms and drowns out any radio message the spacecraft tries to send home. The team had always known this blackout was coming. They had planned for it, accounted for it, built the whole mission around it. But there is a wide gap between knowing something will happen and actually sitting in the room while it unfolds, while the last data fades and the screen goes still. And there is a harder truth buried inside that silence, one that made the waiting worse. During the blackout, the team could not send any commands either. The connection did not just go one way, it went dark completely. The probe was entirely on its own, flying only on instructions that had been loaded into it ahead of time, making the closest and most dangerous pass of its life, with no one able to reach it, correct it, or rescue it if anything at all went wrong. If a problem arose in those hours, no one on Earth would even know until it was long over. All the team could do was wait for the machine to come out the other side and tell them, somehow, that it had lived. Consider, for a moment, where it actually was. 3.8 million miles from the surface of the sun, moving at 430,000 miles an hour, flying entirely on its own through the outer atmosphere of a star. To feel just how close that is, hold it against the planets. Mercury, the innermost world in our solar system, the one that orbits nearest the sun, never comes within 28 million miles of the solar surface. The Parker Solar Probe was more than 7 times closer to the sun than Mercury has ever managed to get. It had gone somewhere no planet dares to go, and back on Earth, in that control room, there was nothing to see but a silent screen, and nothing anyone could do but wait and hope and count the hours. And there is one more detail that makes the closeness land. At that distance, even light and radio, the fastest things in the universe, take time to cross the gap between the probe and Earth. A message from the spacecraft is already old by the time it arrives. So even when contact resumed, the team was not hearing the probe as it was in that instant, but as it had been minutes earlier. Across those millions of miles, they and their machine were always separated, not just by space, but by a small slice of time. It is worth imagining the human side of that wait, because it is easy to talk about spacecraft and forget the people. Somewhere in that control room were engineers who had joined the mission fresh out of school and were now years into their careers. There were scientists who had staked their reputations on the idea that this was possible at all. They had built a machine, taught it to protect itself, sent it toward the one place everyone had always said was off limits, and then, at the most dangerous moment of its life, they had gone deaf and blind to it. All they had left was trust in their own work and the slow passage of 2 very long days. For 2 full days, there was no word at all. And then, on the evening of the 26th of December, something finally appeared on the screen. It was a small thing in itself, a beacon tone. Not science data, not photographs, not a message in any real sense. Just a basic radio signal reporting on the spacecraft's health. But that small signal carried everything the team had spent 2 silent days waiting for. In plain terms, it said, "I am here, I am working, everything is normal." The machine had flown into a star, and it had come back to tell them so. It is hard to overstate what that view from the inside represents. For as long as human beings have studied the sun, and we have studied it for thousands of years, we have done so from a distance, squinting across the gulf of space at a star we could never approach. Every fact we knew about the corona had been gathered from far away, inferred and reconstructed from light that had traveled millions of miles to reach us. And then, in a single mission, that changed. Suddenly we had measurements taken inside the atmosphere itself by an instrument that was physically there, surrounded by the very thing it was measuring. And there is a reason the mission has leaned so hard on releasing real images. In an age when people are, rightly, cautious about what to believe, when so much of what we see can be generated or faked, the value of an actual photograph goes up. These pictures are not simulations or artists' renderings dressed up to look convincing. They are light that genuinely left the corona, passed into a camera flying through it, and was recorded and sent home. When the mission shows you the birthplace of the solar wind, it is showing you a real place, seen for the first time, and that is a large part of why the images landed the way they did. And here is the moment I find hardest not to smile at. The room, by every account of that evening, erupted. Engineers and scientists who had poured years of their careers into this one mission finally let themselves feel, all at once, the relief they had been holding back. There is something deeply human in that moment. A crowd of people who had built a machine, sent it somewhere they could not follow, lost contact with it, and then heard it call back across millions of miles to say that it had made it through. For a few seconds, it was not about data or physics at all. It was about a thing they had made, alive on the far side of fire. Then, in early January of 2025, the real reward began to arrive. The science data started downloading to Earth, and it carried something no one had ever held before, a view of the sun's corona from the inside. Not through a telescope pointed across 90 million miles of empty space, the way every previous generation of scientists had been forced to study it, but from within the atmosphere itself. We were, for the first time, looking at the sun from the inside out. One instrument in particular changed what we could see. It is a wide-field camera called Whisper, and cleverly, it does not stare straight at the sun. Instead, it watches the material streaming off the sun just as it peels away. And its images captured something that had, until then, lived only in theory: the solar wind actually being born. You can watch the plasma lifting away from the corona, organizing itself into the streams that will one day sweep past Earth. For the scientists studying it, the feeling was something like spending an entire lifetime observing a great river hundreds of miles downstream, learning everything you could from afar, and then, finally, standing at the hidden spring where it begins and watching the very first water rise from the ground. And these were not vague smudges or distant glimpses. In July of 2025, NASA released the closest images of the sun ever taken, the sharpest look yet at that boundary where the solar wind is born, showing structure and detail no instrument had ever resolved before. This matters because people are right to be skeptical of grand claims with nothing to show for them. These are not artists' impressions or computer imaginings. They are real photographs, taken from inside the atmosphere of the sun by a camera that was actually there, and anyone can go and look at them. If a story like this is the kind of thing you want more of, a quiet tap on the like button genuinely helps other people find it. And if you have ever found yourself wondering about the sun, here is a question worth sitting with as we go on. If you could send a single question along with that probe down into the atmosphere of the star, what would you most want it to answer? There is a lovely irony in how the camera does its job. To photograph the material coming off the sun, you might think you would point your lens straight at the star, but that would flood the camera with blinding light and reveal nothing. Instead, Whisper looks slightly to the side, catching the faint plasma as it streams away, in much the same way you might hold up a hand to block a bright bulb so you can see the room around it. It is a small, clever trick of design, and it is the reason we can now watch the solar wind take shape at the place it is born. Because the data that came back did far more than show us the solar wind being born. It began quietly answering questions that had stood open for decades. Some of what the probe found was not what anyone had expected to see. Take the coronal mass ejection, one of those huge eruptions of magnetized plasma the sun flings out. When we picture one, we imagine it all flying outward, away from the sun, racing off into space. But the probe captured something stranger than that. Not all of the material actually escapes. Some of it loops back around, caught and pulled inward again by the sun's own magnetic field, folding back toward the star it just came from. Scientists have taken to calling this the solar wind U-turn, and watching it happen up close, from the inside, helps explain a long-standing puzzle: why some solar storms end up so much more powerful than others, depending on how this returning material feeds into what comes next. What makes findings like the U-turn so valuable is that they are the kind of thing no one could have confirmed from a distance. From near Earth, a coronal mass ejection is something you detect after it has already left the sun and started heading your way. You see the aftermath, not the birth. Flying through the region where these eruptions form, the probe could watch the process itself unfold. Which parts of the plasma break free, which parts fall back, and how that feedback shapes whatever the sun throws out next. It is the difference between studying a storm from the wreckage it leaves behind and standing in the clouds while it forms. None of this arrives as a single tidy headline, and that is worth being honest about. The corona is turning out to be a place of overlapping processes, where several mechanisms work at once, and no one of them is the whole story. But that is how a real mystery gives way, not in one clean stroke, but in accumulating pieces, each new pass adding a little more resolution to a picture that had been blurry for 80 years. The probe is not handing us a final answer so much as slowly bringing the question into focus for the first time. Then there are the switchbacks, those sharp zigzag reversals in the sun's magnetic field that the probe had been running into all the way in. From outside, they had looked like a strange curiosity, but from inside the corona, they started to look less like a curiosity and more like a genuine clue. The evidence now points to switchbacks as one of the mechanisms actually carrying energy up from the sun's surface into the corona, helping to heat that thin outer air to its millions of degrees. The picture is not a tidy one. It seems to involve a whole tangle of magnetic events and turbulent waves acting together, rather than any single cause. But this is real progress. After 80 years of a blank wall, the coronal heating problem is finally, slowly, beginning to yield. The probe even helped sort the solar wind itself into families. Getting close enough to see clearly, it confirmed something scientists had suspected, that the slow solar wind comes in at least two distinct kinds. One is threaded through with those small switchbacks, the other is smooth, without them, and each appears to rise from a different kind of region on the sun's surface, born in a different way. These are exactly the sorts of fine distinctions you can only draw from the inside, up close, and they are precisely the pieces the old models had been missing all along. Think about what it means to sort the solar wind into distinct kinds. For decades, the solar wind was largely one thing in our models, a stream of particles blowing outward. Now, from the inside, it resolves into a more detailed picture: fast wind and slow wind, smooth wind and wind rippling with switchbacks, each apparently tied to a different kind of region on the sun. This is what getting close does. It takes something we treated as a single phenomenon and reveals it as a family of related but distinct processes, and every one of those distinctions is a new handle on how the sun actually works. Findings like these are a reminder of why going there in person, or at least sending a machine in person, matters so much. You can learn a great deal about the sun from a safe distance, and we have. But some things only reveal themselves up close, in the fine detail that distance blurs away. The U-turn of returning plasma, the true character of the switchbacks, the two distinct flavors of slow solar wind. None of these could have been pinned down from near the Earth. They are the reward for closing the distance, for actually flying into the thing you have spent generations studying from afar. But of everything the probe recorded, there is one finding that, by all the old rules, should not have been there at all. Something that, according to everything we thought we knew, could not survive so near the sun, and yet the data insisted it was there. For a long time, scientists assumed that dust could not survive close to the sun, and the assumption seemed reasonable, even obvious. In an environment that hot and that violent, any tiny grain of dust should be destroyed almost instantly, vaporized long before it could ever matter to anything happening in the corona. So for years, dust was mostly left out of the story entirely. It was treated as fragile debris that the sun would have burned away, not as a player in the physics of the region. The way the discovery happened is itself a small lesson in how science actually works. No one set out to find dust near the sun. The probe was built to study magnetic fields and particles, and its antennas were meant for other work entirely. But nature does not confine itself to the questions we plan to ask. The tiny voltage spikes from vaporizing grains showed up in the data whether anyone was looking for them or not, and a curious researcher noticed and followed the thread. Some of the most interesting findings in science arrive exactly like this, as something unexpected, caught at the edge of an instrument built for another purpose. It is also a reminder to hold new ideas gently in both directions. The old assumption that dust could not survive there felt obvious and turned out to be wrong. So it would be a mistake to now swing to the other extreme and treat the dust as the confirmed answer to the coronal heating problem. It is a promising possibility, supported by real data and a serious peer-reviewed study, and it is also still unproven. Good science lives in exactly that space, taking a surprising result seriously without rushing to declare victory and letting the next round of observations decide. But nature, as I love about this story, rarely respects our assumptions. The Parker Solar Probe quietly complicated that one, and it did so despite carrying no dust detector at all. The mission was never designed to hunt for dust. What the probe has instead are sensitive antennas. And it turns out that when a grain of dust strikes the spacecraft at these tremendous speeds, the grain vaporizes on impact and briefly releases a small puff of charged particles. That little burst registers as a tiny, sharp spike of voltage in the antennas. So without anyone ever intending it, the spacecraft became a dust detector by accident, recording the unmistakable fingerprints of dust grains in a place that was supposed to be far too hot and too violent for any of them to exist. The dust was there, the old assumption was wrong. In July of 2026, researchers at the University of Alabama in Huntsville took this much further, publishing a study in a respected peer-reviewed journal, the Astrophysical Journal. Their proposal is a bold one. They argue that these charged grains of dust may not be passive debris at all, drifting along and getting in the way. They may take an active part in how energy actually moves through the corona, and could even turn out to be one of the missing pieces in that 80-year-old coronal heating puzzle. The very thing everyone assumed was irrelevant might be part of the answer. The idea works in two competing directions, and the tension between them is exactly what makes it interesting. On one hand, the mass of the dust grains tends to slow the sun's magnetic waves down, allowing their energy to travel farther out before it fades away. On the other hand, The electric charge carried by those same grains can do almost the opposite, concentrating energy and depositing it as heat right where the grains happen to be. If the mass effect wins, energy spreads across a wider region. If the charge effect wins, heat gathers locally in tight pockets. Which of the two dominates could genuinely shape how we come to understand the whole corona? And notice how gracefully the spacecraft turned a limitation into a discovery. It had no dust detector, which by rights should have meant it could say nothing about dust at all. Instead, the very impacts that might have been dismissed as noise in the data became the evidence. Every tiny grain that struck it and flashed into charged vapor left a mark the antennas could read. A machine built to listen to the sun's magnetic voice ended up, almost as a side effect, taking a census of the dust no one thought could be there. It is a reminder that a well-built instrument often tells you more than you designed it to ask. Now, it is worth being careful and honest here, because this is where science is actually being done, at the edge of what is known. This is a hypothesis, not a settled fact, a promising new direction that will need a great deal more observation before anyone can confirm it. It may hold up, and it may not, but even as an open question, it captures something essential about this entire mission. The difference between a thing merely surviving near the sun and a thing actively shaping what happens there changes everything about how we see it, and it leads naturally to another question, one that looks not back at the sun, but forward into the future. If a single probe could learn this much in just a handful of passes, how much farther could a machine like it one day go? So how far could this really go? That question leads somewhere genuinely surprising. The same sun that destroys almost everything that drifts too near it could, in principle, become the most powerful launch pad our species has ever used. The destroyer could become the catapult. There is a poetry to the idea that the sun, the very thing that nearly destroys these probes, could also be what launches the next generation of them into the depths of space. We tend to think of the sun as an obstacle to be survived, but gravity is a tool as much as a hazard, and a star's gravity is the most powerful tool of its kind anywhere near us. Diving close and using that pull as a slingshot turns the danger inside out. The same fierce gravity that threatens to tear a spacecraft apart becomes the engine that flings it toward the stars. Still, it is important not to let the excitement outrun the reality, and the people who study these ideas are usually the first to say so. A concept on paper is not a spacecraft in flight. The shields that would make these maneuvers survivable do not yet exist in a finished form. The missions are sketches of what might one day be possible, not plans on a launch schedule. Part of telling this story honestly is keeping that line bright, celebrating the imagination without pretending the hard engineering is already done. Some scientists have studied a maneuver that would send a spacecraft diving in very close to the sun and then firing its engines at exactly the right instant, using the star's immense gravity as a slingshot to hurl it outward. The idea is called an Oberth maneuver, and the numbers it promises are staggering. Done right, it could fling a probe out toward the very edge of the solar system at speeds we cannot reach any other way, carrying it past Pluto in as little as 3 years. For comparison, that same journey to the outer solar system currently takes spacecraft around a decade. The sun, used carefully, could cut the trip by more than half. What almost kills a probe on the way in could throw the next one to the doorstep of interstellar space. But getting close enough to pull off a trick like that would demand heat shields far beyond anything we have built so far. Researchers have explored ideas like ultra-reflective coatings designed to bounce away almost all of the sun's energy, and layered shields that could let a future probe survive even nearer to the surface than Parker can reach today. And here, it is important to be honest about where the line falls. These remain concepts. They have not been built, they have not flown, and there is a real and meaningful difference between what we have actually done and what we can still only sketch on paper and imagine. It is easy, in a story like this, to let the dream blur into the achievement. They are not the same thing. It is worth letting the scale of that possibility sink in. The outer solar system is so far away that our fastest missions have taken the better part of a decade just to reach it. To imagine cutting that to 3 years, by borrowing a shove from the sun itself, is to imagine a genuine leap in how far and how fast we could travel. The same star that sets the hardest survival problem in spaceflight might also hold the key to reaching places that are, for now, agonizingly slow to get to. That is the strange gift hidden inside all this danger. There is something worth sitting with in that reversal. For most of the story, the sun is the adversary, the thing that melts, that burns, that forces every clever trick of engineering just to survive a few hours near it. And yet the same immense gravity that makes it so deadly is also the most powerful natural engine within reach. A star does not only destroy. Handled with enough skill, it can give a push no rocket could ever match. The line between hazard and tool turns out to be thinner than it looks, and learning to walk that line is exactly what missions like this one teach us how to do. Even Parker's own future is not fully written. Having completed its record-setting passes through 2025, the mission's next steps are formally under review, and one day, not too far off, the spacecraft will begin to run low on the fuel it needs to keep its shield precisely aimed at the sun. When that happens, the story of this particular machine will draw toward its close. But the possibilities it has already opened are real and lasting. And while the far horizon of throwing probes to the stars is still a dream, the data the Parker Solar Probe is gathering right now, on every pass, is already doing something very concrete for all of us, here on Earth. To understand why we spend so much effort watching the sun, I want to take you back to the single most powerful solar storm in recorded history, an event that struck a world far simpler than ours and still left a mark. Just before noon on the 1st of September, 1859, an English astronomer named Richard Carrington was doing what he did most clear days, sketching sunspots as he projected the sun's image onto a screen. Suddenly, 2 brilliant points of white light flared up among the dark spots, so bright and so sudden that at first he thought a beam of ordinary sunlight had broken through his equipment. It had not. Carrington, along with another observer named Richard Hodgson watching independently, had just become the first human beings to witness a solar flare, a violent eruption on the surface of the sun, caught in the act. What Carrington could not have known was that the sun had just hurled an enormous cloud of magnetized plasma directly at the Earth. Today we would call it a coronal mass ejection. It crossed the gulf of space in well under a day, far faster than usual, and slammed into the planet's magnetic field. What followed was unlike anything before or since in the age of technology. The skies erupted in color. Auroras, normally confined to the far north and far south, blazed across the world, reaching as far south as the Caribbean, Colombia, and Hawaii. In some places, the glow was so bright that people rose in the middle of the night, believing it was dawn, and newspapers reported that one could read ordinary print by the crimson light in the sky. Birds began to sing. Miners woke and started making breakfast, fooled by the false morning. But the beauty came with a bite, and the bite fell on the one piece of electrical technology the world had in 1859, the telegraph. Across Europe and North America, telegraph systems convulsed. Currents surged through the wires with no storm cloud in sight. Operators received electric shocks. Sparks leapt from equipment. In some offices, the streams of sparks set the telegraph paper alight and started small fires. Strangest of all, some operators found they could disconnect their batteries entirely and keep sending messages using nothing but the electric current the storm itself was pushing through the wires. The sky had turned the continent's communication network into an instrument it did not control. What makes the Carrington event so useful to us now is precisely that it happened, and was recorded, and cannot be waved away as speculation. It is not a worst-case scenario dreamed up by nervous planners. It is history. A storm of that magnitude has struck the Earth before, within the era of written record, and we know roughly what it did. The only real question is what a storm of that size would do to a civilization that has, in the years since, come to run on the very kind of technology that storm loved to disrupt. That is the question the Parker Solar Probe is helping us learn to answer before we have to face it for real. There is a detail in the old accounts that stays with you. In the hours of that storm, some telegraph operators discovered they could unplug their batteries entirely and still send messages, powered by nothing but the current the sky itself was forcing through the wires. Think about what that means. The aurora overhead was not just a light show. It was pushing so much electrical energy into the ground-based network that the network could run on the storm alone. Now picture that same invisible force flowing not through a handful of telegraph lines, but through the vast web of high-voltage power lines that crisscross a modern continent. Lines never built to absorb a jolt from the sky. That is the scenario that keeps space weather scientists awake. And it is exactly the kind of event Parker's data is meant to help us see coming. Now carry that forward to our own time, and the reason for concern becomes clear. In 1859, the telegraph was nearly the whole of humanity's electrical footprint. Today, we have wrapped the entire planet in power lines, satellites, timing signals, and delicate electronics, and we depend on every bit of it. A storm the size of the Carrington event striking our world now would not merely start a few fires in telegraph offices. It could overwhelm power grids across whole continents at once. This is not a story about the past. It is a warning about the future, written more than a century and a half ago. And it is a large part of why understanding the sun's moods, up close, matters as much as it does. Step back then to the solar wind and to those storms that can reach across space and touch our planet, because this is where the whole mission comes home to ordinary life. Right now, when a major solar storm is heading toward Earth, we get very little warning. Somewhere between 15 minutes and a few hours, depending on the storm. That is barely enough time to switch satellites into a protective safe mode, and nowhere near enough time to shield the larger, slower systems we all depend on down here on the ground. It is easy to hear talk of solar storms and file it away as something distant and unlikely, and for any given week, that is a fair instinct. But the reason scientists take it seriously is that the cost of the rare bad event is so high. Our entire way of life now rests on a web of electronics and long conductive lines, the very things a severe storm disturbs. We have never had a Carrington-scale event strike a fully modern grid, which means, in a sense, we do not yet know exactly how bad it would be. Better warning is how we keep that particular question hypothetical. And this is what ties the whole mission back to the ground beneath our feet. It is tempting to see a probe flying into the sun as pure adventure, science for its own sake, and there is nothing wrong with that. But the payoff is also deeply practical. Every measurement of how the solar wind is born, every glimpse of an eruption at its source, feeds into models that could one day give us days of warning instead of minutes. The machine circling the sun is not only satisfying our curiosity, it is helping to protect the fragile, wired world we have built. And the stakes in this are not hypothetical or far-fetched. We have a real example to look back on. In 1859, a solar storm, now known as the Carrington event, struck a world that had only just begun stringing up telegraph wires, and it set some of those wires sparking and even shocked the operators working them. That was in a world with almost no electrical technology to speak of. A storm of that same size striking our world today, wired and connected and dependent on electricity in every corner as it now is, could push cascading failures through power grids across whole continents at once. Recovery, by some estimates, could be measured not in hours or days, but in months, at a cost that would dwarf almost any other natural disaster in history. It is a rare threat, but not an imaginary one. And this is where the probe's work quietly becomes something more than wonder, more than beautiful images of a star. By seeing directly how the solar wind forms at its source, how those eruptions behave in the place where they are born, and how the sun's magnetic structures build up in the moments before they let go, scientists can begin to forecast space weather the way we have learned to forecast weather here on Earth. Not by scrambling to react as a storm is already arriving, but by seeing it coming well in advance. The goal is to move from 15 minutes of warning toward whole days of it, and that difference, minutes into days, could be enough to protect the satellites overhead, the power grids beneath our streets, and the countless invisible systems that quietly hold modern life together. It is worth naming what is quietly radical about this whole endeavor. For almost all of human history, the sun was something that happened to us. It rose and set, it warmed the crops, and on rare occasions, it threw down an aurora or a storm, and there was nothing anyone could do but watch and wonder. We were entirely passive before it. What a mission like Parker represents is the beginning of a different relationship, one where we do not just endure the sun's moods, but begin to understand and anticipate them. It is the difference between being at the mercy of the weather and learning, at last, to read the sky. And yet, for everything the Parker Solar Probe has already given us, for all the questions it has begun to answer, the machine has not answered everything. Some of the deepest questions it went to ask are still open. After 80 years, the coronal heating problem is no longer a blank wall. We have real pieces of it now. The switchbacks appear to be part of the answer, carrying energy up into that superheated outer air. The dust may be another part, in a way no one saw coming, but no one can yet say they hold the whole of it. And some of the newest clues, those charged grains of dust that were never supposed to be there in the first place, are only beginning to be understood at all. Whether they really do help heat the corona, and how much, is a question that only closer passes and sharper instruments will be able to settle. The answer is out there, waiting, somewhere in the next set of data. There is a quiet dignity in this kind of work. It does not make dramatic headlines most weeks. It is patient, incremental, and largely invisible to the people it protects. But the goal behind it is enormous: to see the sun's most violent moods coming far enough in advance that we can prepare, rather than being caught unaware. Every pass the probe makes, every stream of data it sends home, is another small step toward a world that can read its own star well enough to stay one step ahead of it. And notice how the whole arc of this story bends toward that goal. It began with an unexplained line of light in an eclipse, wandered through a rejected paper and a 60-year wait, survived a shield tested to 3,000 degrees and a 2-day silence on Christmas, and it ends here, on the ground, with something as practical as protecting the lights in our homes. That is often how the deepest science works. It sets out to answer a question asked purely out of wonder. Why is the corona so hot? And somewhere along the way, the answer turns out to matter for the ordinary business of keeping a modern world running. And there is a fitting symmetry in where the story leaves us. It opened with an idea that was rejected on paper, Eugene Parker's solar wind, and with a mystery hidden in a single misread line of light. It passes through 60 years of waiting, a shield tested against 3,000 degrees, a silence on Christmas that lasted 2 days, and dust that was never supposed to be there. And it arrives at a machine still circling the sun, still sending home its fragments of answer. The questions that began all of this. Why is the corona so hot? What drives the wind that touches our world? Are not fully closed, but for the first time, we are asking them from the inside. And that is where things stand tonight. A machine built by human hands is still out there, still falling toward the star again and again, and each pass it makes brings home another fragment of the answer, and, almost always, a fresh question to go with it. For thousands of years, we looked up at the sun and treated it as something beyond our reach, a thing to be watched from a safe and respectful distance. Now a small craft, no larger than a car, is circling inside its atmosphere, patiently listening, and the sun, one pass at a time, is slowly beginning to give up the things it has kept to itself for so long. So let me leave you back where we began, on that quiet evening, with the sun sinking toward the horizon and its warmth on your face. I hope the next time you feel it, you might think of what that warmth really is. Light born just above a corona we are only now learning to read, carried across 93 million miles of space to reach you. And I hope you find yourself wondering, as I do, about the question the probe has left hanging out there in the dark, whether those grains of dust that should not be there are quietly helping to heat a star and what else the sun is still keeping from us, waiting for the next machine brave enough to fly in and ask.